Welcome back, folks, to another JLand Bio exclusive video. Now, you may seem a bit surprised because 9 does not come after 7, and you would be correct, okay? The fact of the matter is we're going to skip Unit 8 for now and come back to it just for time purposes. I want to get this done before we start spring break, so we're going to go ahead and move on to Unit 9, which is Applications of Thermodynamics. So we're going to take all the stuff that we talked about in Unit 6 and Unit 7 and kind of combine that together to talk a little bit about how thermodynamic processes impact equilibrium. We'll talk about entropy, enthalpy, as well as Gibbs free energy in relation to how that correlates to equilibrium. So we have quite a bit of student learning objectives for today. You should be able to understand that entropy is a measure of disorder. You should be able to calculate and determine entropy values, use entropy and enthalpy values to determine spontaneity of a reaction, and understand and calculate changes in Gibbs free energy from enthalpy and entropy. So lots of new vocabulary terms there, but I'm super excited. I think you guys will get you guys will enjoy this. So let's go ahead and move on. Now, the question that we get kind of towards the end here is, so what's left? We've talked about a lot of stuff about reactions. You know, in Unit 6, we talked about energy of reactions. We talked about how energy is stored in bonds and that enthalpy is the measure of the change in heat content of a system. You know that if delta H is positive, that it is an endothermic reaction, meaning energy is absorbed, and if it is negative, that it is exothermic, meaning that energy is released. Remember what we talked about in terms of making and breaking bonds in regards to that. If we break chemical bonds, energy has to go into the system. Therefore, it is endothermic, and if we make chemical bonds, that releases energy, so therefore it is exothermic. We've talked about reaction rate, that is the speed of chemical reactions. We've talked about kinetics, you know, lower activation energy, faster reactions. We've talked about building reaction rates in regards to concentration and things like that. How far towards completion do reactions occur? We know about equilibrium. If K is greater than 1, then the reaction proceeds towards the products. If it is less than 1, then it proceeds towards the reactants. But the last step of all of this is, why do reactions actually happen? And that has to do a lot with the quantities of enthalpy, entropy, and what we'll soon find out is Gibbs free energy. Now, spontaneous processes happen without any outside intervention, meaning that there's no extra energy that has to be input into the system in order for the spontaneous process to occur. So think about rolling a ball down a hill. If a ball just sits there and it will roll down the hill, there's no extra energy that needs to be input in order for the ball to roll down the hill. Same thing with heat moving from hot to cold. No extra energy has to be input. It just kind of naturally does it on its own. That's what I mean by spontaneous reactions. Now, spontaneous does not necessarily mean fast. If we're talking about the speed of a reaction, then we want to focus on kinetics, which is a little bit different than focusing on spontaneity. Now, when we focus on this, we're talking about entropy. Entropy is the measure of disorder. So the greater disorder, the larger the entropy. Entropy is positive, which is S, when entropy increases, and it is negative when entropy decreases. So think about states of matter, for example. Gas has a large amount of entropy. Reason being is that those molecules are moving very rapidly. There's a lot of disorder. They're very far apart, and they're moving in random directions. Next would be liquid. The molecules are closer together, so there's less random movement. They're all kind of in one location, but they are moving around quite extensively. Solid, remember those solid molecules are really close together. They're vibrating in place, so they have relatively low entropy when compared to liquids and gases. So kind of keep those things in mind, that we can determine increase and decrease in entropy by looking at the states of matter of a chemical reaction. Entropy increases when melting and boiling phase changes occur. Melting, we're going from ice to water. So the disorder increases because we're going from a solid to a liquid. The same thing with boiling, we're going from a liquid to a gas. Entropy increases when we form more complex molecules. You know, there's a lot more detail that's associated with that, but you know, molecules tend to vibrate even within their own molecules, the atoms do. And so more complex molecules tends to mean more disorder. Solids or liquids dissolving into solvent. We've talked about that as well, is that when you dissolve a solute into a solution, you dissolve a salt. We increase the entropy because there's more disorder in the system. Or you increase the moles of gas. That increases entropy as well. So if we're looking at just gases on the left side and the right side, if there are more moles of gas on the right side, then the entropy increases. If there are fewer moles on the right-hand side, then entropy decreases as the reaction takes place. So our job here is to predict the sign of the entropy change for each of the following processes. So let's start with number 1A. Solid sugar is added to water to form a solution. Well, we talked about this solution formation. Anytime we dissolve something, delta S is going to be positive. right? Because there's more disorder in the system that we're looking at. Those sugar molecules are now dispersed throughout the solution, so therefore entropy increases. Iodine vapor condenses on a cold surface to form crystals. Well, we are going from a vapor, which is a gas, to crystals, which is a solid. So there's more order within the system, so delta S here is actually going to be negative. Let's look at C. We start with a solid, and we end up with a solid, but we also end up with a gas. Okay, solids I'm not too terribly worried about, but we end up with that gas. So because we're going from a solid to a gas, the amount of disorder increases, so therefore delta S is positive. Now here, if we take a look at this, we have all gases here, but we have 4 moles on the left side and 2 moles on the right side. So there are fewer moles on the right-hand side, which means there is less disorder, so therefore delta S is negative. Number 2 here says, which of the following has the greatest increase in entropy? So number 1, we're going from a solid to a gas. Here we're going from 2 gases to 2 gases, so 2 moles. So the change in actually delta S here is very, very small, probably almost 0. Here we're going from a solid to a liquid, so you have to ask yourself, which has the greatest increase in entropy? Going from a solid to a gas or from a solid to a liquid? And hopefully you said solid to a gas. That's the greatest increase in entropy. Whereas this does have an increase in entropy down here at the bottom, but it's not as much as the one at the top. So my answer is going to be letter A. Okay? So entropy is pretty straightforward to figure out. Just think about what's going to result in more disorder over time. So, we're scientists. We want to know specific amounts of entropy change. So in that case, we can actually solve for delta S relatively easily by taking the entropy of the products and subtracting the entropy of the reactants. So very similar to delta H in that aspect. It's almost the exact same process, but be careful because entropy is measured in joules over Kelvin times moles. The others are typically in kilojoules, so just be aware of that because you may need to make some changes when we start talking about a different equation here in just a moment. So here we're going to calculate the delta S at 25 degrees Celsius for the reaction below given the standard entropy values. Now you'll always be given those just like delta H in your other AP chemistry questions. So we need to do some math here to determine delta S. So our products, SO2, we have a S value of 248 kilojoules per mole. Okay. Now keep in mind, we take our moles into consideration here, so we're going to multiply that by 2, added to 2 times NiO, so we got 38 here. And we get that, we're going to subtract 2 times 53 for nickel 2 sulfide, and then we're going to add to that 3 times oxygen, which is 205. Okay, and same as just before, we plug that into our calculator and solve. And what we end up with here is a negative. So what we end up here is a negative 149 joules per Kelvin. Mole. Okay. So the entropy in this decreases, and that kind of makes sense because if you look at the equation here, all of our solids, we have 2 moles of solids, but then if we look at our gases, we go from 3 to 2, which means that we decrease the number of moles, which, as we talked about, if we decrease the number of moles, we decrease the amount of disorder, so entropy goes down. So pretty straightforward on how to go through and calculate that. All right, let's move on. So the last couple things I want to talk about, first off, is Gibbs Free Energy. And so we've looked at entropy, we've looked at enthalpy, but Gibbs Free Energy is actually the best way to determine if a reaction is spontaneous. Now, delta G is negative for spontaneous reactions, and delta G is positive for non-spontaneous reactions. I know I may have told you something different earlier, but this is the correct one. So delta G, again, is negative for spontaneous reactions, and delta G is positive for non-spontaneous reactions. And we can calculate delta G using Hess's law. We can also use the same formula that we used before, delta G of your products, subtracting delta G of your reactants, okay? So pretty straightforward on how to calculate that as well. Let's do a practice problem. So let's calculate the delta G for this reaction. We have diamond going to graphite using the following data. So if we look here, we've got 2 different equations here. Now, if we look at something like this, you know you're probably going to use Hess's law. We have to rearrange those equations to get oxygen and carbon dioxide to cancel. So we start with diamond here. So this is probably going to be the correct way we're going to orient this equation, this one right here, number 1. Graphite, though, needs to be on the opposite side, so we actually need to flip the equation. So if you remember, with delta G, it's just going to be the same as with delta H, with enthalpy. So when we flip the equation, we actually just change the sign. Okay, so pretty straightforward there. We're just going to change the sign here, and then what we're going to do is we're just going to add those two numbers together. All right, and so what we end up with is -3 kilojoules per mole. Okay, and since delta G is negative, we would say that this process is spontaneous. Because again, that delta G value is negative, so this naturally will happen. Which is interesting because we're taking diamond and we're going to graphite, and you think that it might be the other way around, but you know, 'tis life. So do keep that in mind, that we can use Hess's law for delta G to be able to go through and solve for these types of equations. All right, let's move on to one more thing. So we finally talked about all the different values for thermodynamics that we're going to look at in AP Chemistry. And so this particular equation right here actually gives you the relationship between delta G, delta H, and delta S. Remember, delta G is Gibbs free energy, delta H is enthalpy, T is the temperature in Kelvin, and delta S is your entropy. So by utilizing all of these things, we can determine whether a reaction is going to be spontaneous or non-spontaneous. Let me show you what I mean by that information. So there are a couple different ways that we're going to look at this. We're going to look at this mathematically, of course, but I also want to take a look at it kind of empirically to be able to give you guys a good idea of whether a reaction is going to be spontaneous or non-spontaneous, just based on the positive and negative values of delta H and delta S. So there's 4 different possibilities that we could have here, right? We could say that delta H is negative, while delta S is positive. We could say delta H is positive, while delta S is negative. We could say that they're both negative, and that they're both positive. So think about this just from a sheer mathematical perspective. If delta H is negative, okay, so we'll have a negative value for delta H, and we're going to subtract a positive value from that. Just like I said, we're just looking and plugging generic numbers in the equation up above. If we do that, delta G is always going to be negative, all right? Which means that if delta G is always negative, this is going to be always spontaneous. Meaning that reaction is always going to go spontaneously, because delta G here is always going to be negative. All right, let's look at the opposite here. So let's look at if delta H is positive, right, and we're going to subtract a negative from that, then that value is always going to be positive, okay? And if delta G is always going to be positive, then this is never spontaneous, because delta G is always positive, okay? So those are pretty easy, pretty straightforward to keep in mind, okay? Positive and negatives, one's going to be always spontaneous, the other never spontaneous. Well, that's what happens if both sides are negative. Well, if we take a negative here and we subtract a negative, so this actually is going to depend on delta H or T delta S. So let's just say that this is negative, but it's only negative if delta H is actually greater than T delta S, okay? So this is the only case if delta H is greater than T delta S, otherwise the value is positive. So if we look at it, we know that T is actually involved in this. So we know this value is negative if our temperature is small, okay? Because we're multiplying delta S by T. So if our temperature value is really small, then that makes delta H much greater than T delta S, which results in a negative delta G, which means that the reaction is spontaneous, okay? Now, if we have two positives, the only way that this can be negative is if that second positive is greater than the first one. So this is the case, okay, delta G will be negative if delta H is actually less than T delta S, all right? So this means that this occurs at large temperatures. Okay? So again, this is definitely one of those flashcard moments where we'll need to take a look at this in a little bit more detail. But you should be able to look at these mathematically and determine what's going on here. Again, what we're all looking for in the grand schemes is that value for delta G, whether it's positive or negative. If it is negative, it is spontaneous. If it is positive, it is non-spontaneous. And again, we can look at that mathematically. We can look at that empirically like we just did. Let's do one practice problem just so you guys can kind of see what this looks like from a mathematical perspective. All right, so using the same equation from before, we want to know if a reaction is spontaneous. If delta H is negative 218 kilojoules per mole, and delta S is negative 765 joules per kilograms per mole. So using the previous equation, we want to determine if a reaction is spontaneous if delta H is negative 218 kilojoules per mole, and delta S is negative 765 joules per Kelvin mole at 32 degrees Celsius. Will the reaction become more or less spontaneous as the temperatures increase? So we're solving for delta G here. Okay. And literally we just plug in and solve. So delta H is negative 218 here. We're going to subtract our temperature. Temperature has to be in Kelvin. So we're going to add 273 to that. So that's going to result in 305. Now be careful here. Remember, delta S is in joules. So we need to divide this number by 1,000 in order to get it into kilojoules. Okay? So we're going to multiply this by 0.765. Also keep in mind that this value here is negative. So we plug in our numbers and solve. And we get a positive 15 kilojoules per mole. Okay. And since we get a positive value for that, this is non-spontaneous. Okay. Again, pretty straightforward for that. Now the next question says, will the reaction become more or less spontaneous as the temperature is increased? So again, if you think about it, we're increasing this value here, okay, which is going to give us a more negative value here. So you can do one of two things. You can just kind of think about this empirically. You can plug this number in, but we have a negative, and we are subtracting a negative. Okay, so as this number becomes more negative, the end result actually becomes more positive. So as we get more negative here, we get a more positive result at the end. So this actually becomes less spontaneous, because the delta G value continues to increase. Okay? So again, just some math that's associated with this. It's pretty straightforward to plug in and solve, but remember, the whole goal of this is focusing on if delta G is positive or negative. All right, guys, that just kind of wraps up our video for today. Hopefully you got a lot out of it, a lot of information here, but again, hopefully it's pretty straightforward. We'll just have to practice with it in class. All right, we'll talk to you later, guys. Have a great day. Bye-bye.